be okay to start?
Yes, would you like me to start?
So I'll just do a quick introduction then, just
Sure.
to get things going. So thanks everyone for turning up today. Very lucky to have a talk by Bob Laramee from the School of Computer Science. He's very kind to talk about some of his research around data visualization, particularly in relation to computational fluid dynamics, although hopefully you can branch off into some other topics as well. I'm not going to say much else apart from that this session is being recorded. So if you do have any issues with that, please let myself or Rebecca know. And on that note, I'll pass over to Bob.
Thank you very much, James. Thank you for the invitation. I very much appreciate it. And also thank you to Rebecca for help setting this up. So yeah, the name of this talk is Dynamic Visualization of Computational Fluid Dynamics Data. It is not a conventional talk in the sense that I just throw a bunch of slides at you and then you're dead at the end. The way this is going to work, hopefully, is I give a short introduction to the topic of flow visualization or visualization of computational fluid dynamics data. And then there's a special slide that shows about 9-ish different options, different topics that we could discuss, but we can't discuss all of them. And so in order to decide which direction to go into, I will ask the audience to make a vote. So I'll present the different topics, I'll give a 1-minute introduction to each topic, and then the audience will vote which topic they find the most interesting to talk about. So I hope that everybody is prepared. And James and Rebecca are going to help with this, hopefully. And if you have any questions or comments, you can interrupt at any time. It's perfectly fine. And actually, I prefer it that way. I like being interrupted, and I like it when people make comments, as long as they're polite. Good. I will also make one other note. This is a special topic, this flow visualization topic. And I am the only person in the United Kingdom that studies flow visualization, and I happen to be here at Nottingham. So it's kind of a special occasion, I would say, in that sense. And it's very surprising, like, for me to say I'm the only person studying flow viz in the UK is a weird thing to say. Like, it feels weird, and it shouldn't be that way, but it is right now. So a little bit about my background. So I was born in Boston, Mass. I hope that some of you have heard of that. I have a bachelor's degree in physics from the University of Massachusetts Amherst. Hopefully some of you have heard of that too. Then I did a master's degree. I switched topics to computer science at the University of New Hampshire. And then there's a dashed line there with an arrow. That represents the Atlantic Ocean in this case. And I moved from New Hampshire to Austria, and I wrote a PhD at Vienna University of Technology. Maybe some people have heard of that. And my PhD thesis was actually the visualization of computational fluid dynamics data. So that's actually the topic I've been studying for quite a long time now. After that, I moved to Swansea University, and then I just recently joined University of Nottingham this year, actually, in January of this year, and just before the lockdown. So basically, it's been a really interesting experience, an interesting time to switch universities and switch locations. This is a general kind of motivation behind data visualization. This is not really something this audience needs. I think this audience is very, it's very obvious why data visualization is an interesting topic, but I go through this very, very quickly. So in the world of modeling, right, you're trying to model the real world in software, but you know already that it's much more feasible to model the real world in software before doing it in the real world, in a physical approach, to save money, right? You're all trying to save money before you model things in the real world. So you create this simulation software, right? That's what I call a digital solution. So there's, for every real world challenge, there's a physical approach. And you find out, you discover how expensive the physical approach is. For example, building 1,000 different physical models of a car is very expensive and time consuming and generally not feasible. So then you jump over from the physical world to the digital world. That's what this dashed line is. It's the transition from the physical world to the digital world. In your case, you are designing simulation software. That's your digital solution to model objects in the real world. And from my point of view, this creates another challenge, and that's what I call data chaos. So some of you watching might be generating massive amounts of simulation data, like gigabytes and terabytes of CFD simulation data. And that's a problem, another problem I call data chaos. And a good way to solve that problem or to address that problem is through data visualization. So visualization, being able to see your data, takes away, it reduces the chaos and turns that chaos into order. And that's what I call the cosmos. I think this is something that the CFD engineer is very I don't really need to go into detail. Data chaos, these terms, I'm using them very loosely. Data chaos is a very loose term. It just means you've generated so much data that you're struggling to understand it. And it can be chaotic in many different ways. It can be too big to manage. It can have too many dimensions to manage. It can be physically stored on different devices in a literally chaotic manner. So chaos in this sense just means very, very difficult to manage and difficult to extract useful information and knowledge from. This is the central challenge. Like, you have these massive amounts of data, you have these massive data sets, and now you're scratching your head going, what is the best way to extract useful knowledge and information from them? So it's a very generic term. It's not tied to like chaos theory or something like that. Or entropy. You could talk about entropy. So what is data visualization good for? The strengths, it's good for exploration. This is the case when you are just trying to get an overview of your data. You're not an expert. Somebody else gave it to you, and you're trying to find outliers or patterns or trends. You might not have generated the data yourself, right? This might not be the case for this audience. This audience, I think in this audience, most people fall into the analysis group. This is when you have personally, or somebody you know or work with has generated the data, and you have done so to either confirm or refute a hypothesis, or study some behavior, like the behavior of flow, in detail. You have an expectation about how the flow is going to behave, and you want to either confirm or refute that expectation or that hypothesis. Presentation is after you've done exploration and analysis. You want to then share the results with a wider audience. Maybe it's the public, Maybe it's a group of engineers, maybe it's management. Data visualization is very good for presentation. Two more subtle aspects for that data viz helps with are acceleration and increasing confidence. If you take a step back, what do you do with data? Everybody does one thing with data, and that thing or that verb or that action is search. It doesn't really matter who you are. When you're generating data, you are performing a search process. In your case, you might be searching for expected behavior versus unexpected behavior, or good behavior versus bad behavior. But at one level, this is a search process. This is what people do with their data. And data visualization is very good at accelerating the search process, taking a search process that might be very slow and speeding it up so it can be performed in a matter of seconds. There are also search processes that are impossible, basically impossible without data visualization. So enabling searches, kinds of searches that were previously impossible, is also a strength of data viz. Increasing confidence. As soon as people can see their data or the way the flow behaves, that's a form of verification or validation. And data viz is very good at verification or validation. It often happens that when we apply our data viz techniques to a new data set, that we find errors, right? And correcting those errors leads to increased confidence. Okay, this is where it starts to get a little bit more into detail. This is the so-called, this is a depiction of a flow visualization pipeline. And it goes from left to right. Now, conceptually, this is a continuation of a pipeline that you're already very familiar with. In the CFD world, your pipeline starts with the surface modeling phase. I'm going off to the left, which you can't see because I haven't included the CFD pipeline. It starts with surface modeling. Then the second stage is the volume meshing, taking the surface model and constructing the volume mesh. And then the third stage is simulation, then running the fluid flow simulation on your volume mesh. And then you might have a fourth stage that I think you guys call post-processing. A lot of you might call it post-processing. That's what this is. This is the post-processing phase in a more, let's say, specialized view from somebody that's specializing in just the visualization stage of the pipeline, or the post-processing phase, if you want to call it that. So it starts off, in our world, it starts off with the simulation data. It could be measurement data, it could be modeling data. Then we might do something to the data, like filter it. We might resample it, for example, from an unstructured grid to a structured grid or something like that. Or we might fix errors. We might include uncertainty. We might do some special interpolation on the data. This is the phase we call data enhancement. After we enhance the data, sometimes, by the way, this can also be optional. It's not always even performed. We start what we call the visualization mapping, and that is attaching visualization primitives to the data. Things like glyphs, isosurfaces, color mapping, streamlines, all the things that you can actually see, right? And then we perform a rendering process. This is where we use computer graphics to efficiently render the data. We might apply shading, animation, visibility calculations, projection from 3D to 2D. These are all things that computer graphics deals with. And then we offer a set of interaction techniques. So at the end of the pipeline, there's a person, which is not shown here. there's a person and they have their perceptual system, and then they can interact with the scene or the images that they see, and then change those images depending on different parameters, either visualization parameters or input parameters like threshold, seating position, slicing. When there's an interaction, we move back to the data enhancement phase possibly, and we revisit the pipeline and the scene is updated. So it's a continuous loop. That's the flow visualization pipeline. The data can be mapped to color, textures, opacity, positions, different sizes, different thicknesses, different shapes or curves. This image, some of you might be familiar with this style of visualization. It might be new for some of you, but this is flow that's being depicted by a texture, by a dense white noise texture. We're looking down at these are two an intake port and an intake valve, outtake valve. This is a combustion chamber from a motor simulation, and the texture is being smeared in the direction of the flow just underneath the surface of that geometry. And here, one of the advantages of this technique is we can zoom in. This is a zoomed in version, and we can get more detail about the behavior of the flow. Also, the flow velocity is mapped to color. So the slow flow is this light blue color. Here's some slow flow. And then the fast flow is darker and more red. Here we can see some patches of very fast flow that look sort of like deviant behavior. Here's some more examples. This is a visualization. This is from meteorology. This is the simulation of a hurricane. I don't know if anybody's working on things like that in this group. This is something we called streamline clustering. So we can actually cluster streamlines depending on their behavior and their curvature and their other properties. This is a depiction of a streak surface. I don't know if anybody in this group is familiar with streak surfaces. And here are some glyphs to show the behavior of flow. In the same example as our previous slide, but this time it's a side view. Okay, that's the introduction. So that's the where I sort of just show lots of slides and then you have to sit through that. This is the part where we can go in, let's see, 1, 2, 3, 4, 5, 6, 7, 8 different directions. So this is the dynamic part of the talk. Dynamic flow visualization directions. So what I'm going to do is I'm going to describe each of these 8 directions in just about 1 minute each. I can see there are already votes. And then the audience is going to vote on which topic they'd like to hear about. We won't be able to talk about all 9 of them, or all 8 rather. We'll only be able to talk about maybe 1 or maybe 2. And the audience will essentially will vote and will. So automatic streamline seating, probably you can imagine what that's about. I think you're used to manual placement of seeds where you use the mouse or some sort of a seeding rake and you're trying to position streamline seeds manually on some region of space that you're hoping to understand better. We have worked a lot on automatic streamline seating strategies that don't involve this tedious placement of individual seeds in space. We've also worked on visualization of seating sensitivity. That means that's basically about the sensitivity of the flow field. So sometimes if you move a streamline seat a little bit, it has no effect on the curve, like the curves look the same. But there are regions of high sensitivity, like for example around a critical point, where if you move a streamline seed just a little bit, the resulting streamline is unstable and the curvature can vary wildly. That's what we call seeding sensitivity. The next topic is stream path and streak surface construction. So you can take the idea of a streamline, which is a one-dimensional curve, and extend it to another dimension, which is a surface. So a streamline is a curve that's everywhere tangent to the vector field. A stream surface is a surface that is everywhere tangent to the vector field. And it's not the same as an isosurface. I think you're used to using isosurfaces, which are surfaces of a constant scalar value. That's not what stream surfaces are. They're actually orthogonal to isosurfaces. So we have studied stream path and streak surface construction. How do you actually construct those surfaces? And what do they look like? A great topic. We've also studied automatic stream surface placement. So in addition to construction, which is a challenge for stream surfaces, how can you place them automatically? Very challenging problem, by the way. These are all pretty challenging. This is more applied. This is motor simulation, getting back to the motor simulation. This is actually taking a selection of flow visualization, state-of-the-art flow visualization techniques, and studying the fluid flow through a cooling jacket, which is also challenging, very applied. This is, again, applied, visualizing swirl and tumble motion, taking a set of state-of-the-art flow visualization techniques and studying the two patterns of flow inside the combustion chamber, the pattern of swirl flow, this is the swirl flow example, and the tumble motion example. And these are the combustion chambers inside of your engines, your diesel and gas engines, and seeing what that looks like. Another topic is texture-based flow visualization. So we saw that on a slide, one slide ago, where we depict the flow using textures. And those textures can be dynamic, so we can animate the textures in the direction of the flow, so we can watch the flow. And it has a very organic, fluid-like look and feel. And it's also a very challenging topic. And then we have another special application. This one's very generic. It's a generic research topic. This one goes back to a specialized application. This is a specialized application we developed that combines information visualization techniques with classic flow visualization techniques to come up with what we call knowledge-assisted seeding. So it's a seeding strategy, and the seeds are placed by using the information visualization views, which is very unusual. So for example, the user can say, please seed streamlines in any area of negative velocity. Right? That's a very strange kind of proposition for traditional software. But conceptually, it makes a lot of sense to be able to say, oh, I want to see all streamlines that go upstream instead of downstream. And we present a set of interfaces that allow the users to make these kinds of queries that are natural conceptually, but very unusual in software. Okay, so this is the part where we count the votes.
Some of us are still voting.
So the seeding, okay, we have automatic streamline seeding. It looks like visualization of seeding sensitivity is one. Stream path, streak surface construction. Automatic surface placement has 3 votes. flow through the cooling jacket has a vote. Visualizing swirl and tumble motion has a vote. Texture-based flow viz. Oh, the special application has 4 votes. So there was a tie here between the automatic surface placement and the special application that search for green energy. I don't have a...
Sorry, Bob, there's one more vote on automatic surface placement. I think it's just nudged ahead.
Okay. I was about to say, does anybody want to try to break the tie?
I was going to step in.
Yes, I would have asked you to step in and break the tie.
We'll have to go with democracy.
Now, there's something else I want to mention. We can't talk about all these topics, but you can see all of these topics. So I'm going to show my YouTube channel. I have a YouTube channel. You can search for my name, or you can search for DataViz Bob Laramee. And there are a bunch of playlists on here. And you can see all of these topics. I have 2 playlists. One's called Flow Visualization Research and one's called Flow Visualization Talks. So you can see all of these topics on the DataViz YouTube channel. You don't have to miss anything. So don't be too disappointed if we don't talk about something. They're all here. And look, this playlist has 24 videos, which is quite a lot, and this one has 9. So it's quite a lot of material. And if you want, you can see some other topics as well, like geospatial visualization or visualization for healthcare. Okay, so and the other thing that's different about this part is I deviate away from slides. So instead of showing just slides, I'm showing interactive demos and videos of what's happening. Because slides are not very, they're not very exciting, but videos are much more interesting, live, dynamic videos. Okay, so we said automatic surface placement is the next topic. Whoops. Okay, so we'll go to the automatic surface placement category. So we spent a lot of time developing algorithms that construct stream surfaces, which are surfaces everywhere tangent to the vector field, path surfaces, which are surfaces everywhere tangent to the vector field in an unsteady flow or time-dependent flow, and then streak surfaces, which are not always tangent to the flow. A streak surface is analogous to injecting dye into the flow, right, into real flow. If you inject dye into a flow at one point in space-time, it will trace out a curve, right, that moves with the flow. You can imagine a massless and infinitely thin edge dropped into the flow and releasing dye into the flow. The software equivalent of that is the streak surface. But for all of these techniques, it doesn't matter if it's streamlines, stream surfaces, path lines, path surfaces, you need to figure out where to seed your curves or your surfaces. And how can you do this in maybe a more automated way or a semi-automated way that reveals the important characteristics of the flow? And that's a problem we worked on for several years, actually. This is an overview, another pipeline. I love pipelines, by the way. I love all the scientific viz have pipelines. So the input to the pipeline is a flow field or your CFD simulation. The next phase is we then apply what we call a flow field clustering technique to the original vector field data. In other words, we look at the underlying data, the underlying flow, and then we group areas of flow that have very similar behavior. So if we have laminar flow all pointing in the same direction, we might group that together in its own cluster. If we have a vortex, we will take that vortical flow and we'll group it together in its own cluster. Once we have our vector field clustering performed, we then compute curves that represent each cluster. So every cluster gets its own seeding curve. And the seeding curve will be generally tangent to the flow direction. So you can imagine you don't want a curve that aligns with the flow. If the flow is moving from left to right, you don't want a curve that's left to right. You want the curve to be actually orthogonal to the major flow direction. After we compute the curves, we construct our surfaces. Then there's a rendering phase, and these things can all be iterative. We have interactive user options. Let the user adjust the parameters, all these parameters. And you'll notice we have this curvature field derivation as well. That's to help us make sure that our seeding curves are orthogonal to the underlying flow field. We don't want the seeding curves to align with the flow or be tangent with the flow. We want them to be orthogonal. Okay, let's look at a video of this instead of just a slide. So where are we? Okay, I have a few videos on this topic. Hopefully this will be big enough. Let's see. Make sure that it's nice and big. This is what it looks like when you have the automatic stream surfaces placed in action. In this particular case, we've decided to generate seeding curves along the boundaries of the flow, now of the domain. These boundaries are very special. They're a special kind of boundary, and these boundaries divide the exit flow from the entrance flow. So on one side of the curve, there's flow coming into the domain, and on the other side of the curve, there's flow exiting the domain. And we call these boundary switch curves. And we can use those curves to actually place stream surfaces and then study the properties of the flow. Right? And that's an objective measure by which to look at the flow. It doesn't involve some person trying to navigate the flow field and find out where the interesting flow is. It's a fully automated approach to stream surface seeding, right? It's not the only approach, but it is one approach to that problem. And I'll show the other one. There was no clustering in that example. The clustering example is this one. So this is the one that generates the hierarchical clusters and then uses those to automatically seed surfaces. I hope everybody can see this okay. So these are all the seeding curves, and they're based on the features in the flow. And then as soon as you render the surfaces, the features of the flow turn up. So here we have four vertical structures, right? Four major axes inside the flow, and the flow is actually hinging or moving around these four major axes. So this flow visualization has this nice property that it searches for features in the flow, Then it automatically seeds the curves, and then from those curves, you can seed the surfaces, generate the surfaces. This is flow past a square cylinder or flow past a block, right? And usually one of the areas of interest is that vertical space right after the block, when the flow passes the block. In here, we can automatically generate some curves that capture that location in the flow, and then automatically compute surfaces. We can also change the number of seeding curves. We can actually interactively say, okay, we want to focus on big clusters only, or we want to include smaller clusters. So there's actually a hierarchy of clusters, and the user can actually move up and down the hierarchy depending on the level of detail they want to see in the flow and the number of surfaces they want to see in the flow. This is the Hurricane Isabel simulation. That's one automatic stream surface, or I think it was 3 actually. I think there were 3 seeding curves. This is showing how we can adjust the transparency of the surfaces. So we can make the surfaces semi-transparent, and then we can see through them. And that helps with occlusion, for example, and visual complexity. That's a high number of surfaces. Adding more surfaces and more clusters if we want complete coverage of the flow. So there's always going to be this trade-off between coverage of the flow domain and occlusion and visual complexity. So the higher your coverage is, the more occlusion you'll face and the more visual complexity, and then the lower the coverage, the less complexity you'll have. Maybe I will show that other one. This is also automatic stream surface seeding, since we're here. I really enjoy these videos. This was a PhD thesis, the automatic stream surface seeding. It's actually the only PhD thesis in the world on this topic that's dedicated to the automatic stream surface seeding. So it's really a special topic. These are some of our earlier experiments with the automatic stream surface seeding. This is extracting the features and then using evenly spaced stream surfaces. So you can see that the spacing between those stream surfaces is very consistent. Right? This is one of our early experiments. And then the user is using slicing on the domain to see across the space. So you're all familiar with slicing. That's applying the slicing technique to stream surfaces, so you can see inside the flow domain. That's the vortex core at the center of that's a simulation of a tornado, by the way. And that vortex core is actually captured by a stream surface in this example. Okay, that's the automatic stream surface one. Any questions about that? About the automatic stream surfaces?
I'm just checking one question perhaps. You mentioned this was from a PhD project you're in. Are there any tools available to help people implement this type of thing?
There are tools available, however, they are research prototype tools. Mm-hmm. They are not like off-the-shelf commercially available tools that are designed and engineered for many users. So whoever would, for example, Matt Edmonds, who did the automatic stream surface placement, he left behind his software. but it's a research prototype software. That means for somebody to be able to use it, they would have to have some software development skills. It's not like a commercial piece of software that you can just download and bam, start using.
Yeah.
Because that's not what we get, you know, the funding, to get funding to develop commercial products or products that can be used by hundreds of users or thousands of users is difficult, right? It's very difficult.
Yeah. Yeah, sure. Okay, but they're just a foundational piece of at least research software.
That's right.
So
That's
you
right.
can go and at least play with. And
Yes,
see what, okay.
that's right.
And are you the best point of contact to find that, or would you do Matt Edmonds?
Yes, both of us, yeah.
Thanks.
Okay.
Anybody else have any questions about it?
Any questions about the automatic stream surface placement or any other things so far? Is everything I'm saying making sense? Hopefully. I hope.
Yeah, I think science is agreement there.
Okay, I hope so. I guess silence means it's fine. Should I keep going and do the next one? The search for green energy, since that was the second?
If you've got time, Bob, that would be fantastic.
Yeah, I have no problem with that. We can even do 3 examples. It depends on you guys.
I think it's entirely up to you.
Let's see. This is the application that we developed for a special purpose. In this case, it is the development of marine turbines. Is anybody here connected with any kind of marine turbine simulation? So marine turbines are an alternative to wind turbines. And marine turbines are hiding underneath the surface of the water. And so there's a lot of research being dedicated to maximizing the efficiency of marine turbines. Right, they have some advantages over wind turbines. You know, one of the advantages is that you can't see them necessarily, so they don't alter the landscape, let's say. Another example is that the tides are a more consistent source of energy than, say, the wind. The tides are very predictable and very reliable. And the wind is less predictable and maybe less reliable. Although in the UK, I think the wind is pretty reliable and predictable. But anyways, that's a topic. If you're studying marine turbines, this is one of the arguments you use to support their development. And one of the largest marine turbine experiments in the world is here in the UK, and it's in, anybody know where it might be? I don't know if anybody's connected to this topic at all. One of the largest, yes, that's right, whoever answered the Bristol Channel is correct. Anybody know why it might be the Bristol Channel? The Bristol Channel has, yes, the Bristol Channel has a special property in that it is the biggest tide gradient. It's one of the biggest tide gradients in the world. So there's a lot of water that shifts in and out of the Bristol Channel on a daily basis, on a tidal basis. So it's a great opportunity to extract energy from that. It's basically an exercise. The exercise is very similar. It's taking the kinetic energy provided by the motion of the fluid and trying to turn that into another form of energy, for example, electricity. That's the exercise. It's a similar exercise to the wind turbines. But in the case of the marine turbines, the flow is much slower. And the consequences of that are like the blades are not, they don't look the same. And the blades turn much slower in the marine turbine case. You don't have these very fast rotating blades. So we worked with some computational fluid dynamicists working on the design, the optimization of marine turbines, and they wanted to understand how to place the turbines in space. So they have a ground floor that's submerged underwater, and they're trying to figure out the optimal placement for an array of these marine turbines. And the idea is that they don't want the marine turbines to interfere with each other. So this is an image of the flow past a marine turbine. The blades are not shown in this case, but all of these streamlines are placed at the blades of the marine turbine, and that can be done using these other views. It's not somebody trying to position a rake in space. It's somebody saying, look, I want to, look, there's a table here of blade, this is a table, a histogram. Each row in this table represents a histogram, and the user can actually select the blade histogram and then seed streamlines at the blade, as opposed to trying to position a rake around. This is another view of the same data. These are all views of the CFD simulation data. This is the view you're used to, the spatial view. This is a high-dimensional view of the data we call a parallel coordinates view. That's really, that could be another talk in itself, but it's a high-dimensional view. Each axis in this view corresponds to one CFD simulation attribute, like velocity in the downstream direction, pressure, temperature, and so on. This is something we call a velocity histogram view. So that's actually taking every vector and placing it at the center of a normalized sphere, and then it's a traditional histogram, but it's in a 3D polar space. And you can seed streamlines in that space as well. This is something we call a streamline view. I think this will make a little bit more sense, hopefully, when we show the video. And the advantage of this is we can place streamlines in a logical way. This is the user. So imagine we have this scenario where the user says, I just want to see the areas of reverse flow, because the areas of reverse flow work counter to capturing the momentum of the downstream water, the downstream flow water. With a normal piece of software like TechPlot, how do you do this? How can you say, I want to see areas of reverse flow, or I want to seed streamlines in areas of reverse flow? This is generally not possible, this kind of investigation. Or let's say it takes a lot of creativity. I don't know how to do it in TechPlot. This is somebody trying to do this exercise in TechPlot. They have some rough idea of where they think the reverse flow is, and they're trying to seed streamlines using the TechPlot features to see if they can capture the reverse flow. But it's really difficult. You're not even sure if it's working, actually. But we can enhance that to make this kind of thing very, very easy. This kind of let's say, query. This is the spatial view. This pillar is called a pylon, and that's the structure on which the turbine blades sit. They have to sit on a structure. We never see the turbine blades because they're using a time-averaged blade technique that doesn't show the velocity. And here we see a histogram view of the flow. So there's velocity, there's a velocity histogram. Look, there's a lot of velocity values here. There's a pressure histogram. Most of the pressure values are here. There's a turbulent kinetic energy aspect, and so on. But the velocity view is broken down into three components, the x, y, and z. The x component aligns with the flow in this case. Look, the x direction is the long orientation of this flow domain. So what the user has done is they've said, I've selected the negative x velocity in my histogram view. There it is. Now show me all the streamlines that are seeded from these positions. So it says the reverse flow can be intuitively obtained from the histogram bars which contain negative velocity values. So you can very intuitively, and they also show up in the other views. All of these views are connected to each other. So you can see the properties of the CFD, the other CFD attributes connected. There's the negative velocity showing up in the parallel coordinates view, and then you can see its relationship to all of the other CFD simulation attributes. For example, the pressure or the turbulent kinetic energy and so on. And then there they are. Those are the actual streamlines. And those streamlines are all seated in the areas of negative velocity, and they're all behind the pylon. So as the flow passes the pylon, it creates a vortex, and when it wraps around and comes in the reverse direction, it's automatically extracted, and then the streamlines are seeded. And you can see exactly, okay, this is the area of the flow that the energy is drawn away from the marine turbine. So this is not going to help in terms of capturing the flow and converting it from kinetic energy into electricity. This is going to work against that process. This is the user zooming in on that area. We've used a kind of grid distortion technique, so we can zoom in on the underlying grid and see more details. That's what that view is showing. Now the blades are not represented explicitly in this simulation. They're using something called a time average blade simulation. And the simulation is faster that way. Instead of trying to model the blades individually and then rotate them around, they say, let's do a time average blade simulation. It's a kind of innovative technique, and therefore the simulation runs much faster. However, the drawback is you can't see the blades. But with our software, we can brush the area of the simulation data that represents the blades, and then we can actually see the time average blades in the spatial view where they were originally invisible. And that's what we're seeing right now. The user has brushed the blades in the histogram view. We can visualize the flow, behavior of the flow at the blades using glyphs. Those are glyphs. And then we can see the relationship to all the other CFD simulation attributes in our parallel coordinates view, which is in the bottom left. We can use those positions as seeds, as streamline seeds, and then see how the flow behaves when it hits the time average blade. So this is essentially the interface between when the energy is converted from kinetic energy or momentum into stored energy, like electricity, for example. That's the interface, and that's what happens to the flow. And what the engineers want to know is how far apart do these blades need to be in order to not interfere with one another. So there's a spacing requirement. And they tried to make some guesses. For example, how far downstream do we have to go to regain 90% of our original kinetic energy? That's the idea. Like, and how can we position these to capture convert the most kinetic energy into electricity as possible? And this is a kind of visualization that can help with that quite easily. We can also just use this interface to say, okay, I want to position streamlines in the areas of the most, the flow with the most swirl, with the highest swirling component. And we can use this streamline graph view. Each one of these components here is a streamline, and it's mapped to curvature. You can see streamlines on the x-axis, and then curvature magnitude on the y-axis. And you can see, okay, these are the streamlines with the maximum curvature, for example. And I hope that example made some sense. So it's essentially, to summarize, it's showing alternative views of the CFD simulation software data that you're not used to seeing in an information visualization way. So like the polar histogram, the parallel coordinates view, and the histogram table. And then being able to select different parts of the flow in those alternative views and have them appear in the spatial view. Any questions about that example? I think I've...
Not touching so much, but if possible, could you just maybe talk about the parallel coordinate plots, because I think that would be of interest to quite a few people. Maybe just, I mean, it's a very detailed topic, but just quick.
A quick summary?
Yeah, possibly.
Yeah, I can do that. I am going to...
I'll see if you've got a question from Danson as well.
Okay. Is there any example for unsteady flow? I have definitely examples from unsteady flow. The unsteady flow, there's an example of unsteady flow in the seating sensitivity. There's unsteady flow in the path and streak surfaces. Those are both unsteady. I could have labeled each one of these with steady versus unsteady. This is steady state. There's an example here of unsteady flow. This is an example of unsteady flow. This one is steady state. Yeah. So I could show an example of unsteady flow, or I could go into the parallel coordinates description in a little bit more detail. Do you want to make the decision on that, James?
But we had some interest with unsteady flow, so let's go with that. And I think you've got a lot of resources for the parallel coordinates on your YouTube channel. So
that's right. We have tutorials of parallel coordinates on the YouTube channel, so you can really see full tutorials about those, because we teach that in the DataViz class, and all the lectures from the DataViz class are already on YouTube. It's a great topic. And maybe we can get together again one day and talk about it. I'm going to put my favorite example of the unsteady flow. This is definitely one of my favorites, if not my favorite. This is the visualization of swirl and tumble motion. And it's using a lot of unsteady flow visualization techniques. So this is 1/2 of a valve cycle inside of an engine simulation. And we're seeing the crank angle is shown. What we're actually seeing is engine simulation data. And the engine is composed of combustion chambers and cylinders, valve cylinders. The head of the valve cylinder is actually here. It's at the bottom, but it's not shown explicitly. The explicit surface is the inside of the combustion chamber and the intake ports. And here, we're using something we call a pathlet visualization, which are short path lines to visualize, in this case, the tumble motion of the flow. This is tumble motion. And also, I can mention that this thing has been sliced in half, so we're only seeing half of the cylinder. Here we see a combination of two techniques, right? Unsteady flow vis particles. These green tubes are vortex core lines. So they're lines of, they're the axes of swirling motion, and they're dynamic. So we're actually seeing vortex core lines as they evolve over time, which is not very common, I would say. This is actually a steady state visualization of the flow topology. So all of these spheres are critical points, like sources and sinks and saddles. And then we can visualize the connections between them using, these are all special streamlines that connect the critical points to each other. This is a volume rendering of the flow as well that shows the swirling behavior of the flow, the vortical regions. This is what it looks like when we visualize the time-dependent topology. So each one of these spheres is a critical point. It's either a source, sink, or a saddle. And then these lines connect the critical points to each other, these dark lines. The gold lines are actually, again, vortex core lines. So they're the axes of swirling motion. This is using something called volume rendering. Now each one of these regions is a volume, and it represents swirling behavior. The swirl is in one direction for the blue, and it's in the reverse direction for the red. But rather than trying to isolate it to a fixed point or a fixed curve, it encompasses a region of space. And this is actually the same data on both sides, but with two different flow visualization techniques. This one uses the topology-based flow combined with volume visualization. This uses texture-based flow visualization, which I guess we didn't have time to really go into detail about. But this is texture-based flow viz at the surface of the combustion chamber. Yeah. So that's one of my favorite unsteady flow examples. And again, all of these examples are on YouTube, so I went through that kind of fast. There's a lot of activity in that video, and it goes very quickly. So it's nice to be able to watch it multiple times. I've watched it many times myself, and every time I watch it, it's a lot of information, so it's good to be able to watch it. And YouTube will also let you adjust the speed, so you can slow it down to half speed or quarter speed or speed it up and so on. Yep. Okay, I think that's good enough for today, wouldn't you say, James?
That's been fantastic. Thank you very much for your time, Rob.
Yeah, thank you for inviting me. I hope that you saw some interesting things. Some new things and some interesting things that you might want to, I don't know, talk about in more detail or see in more detail.
Yeah, absolutely. I've got one very general question.
Mhm.
Is it okay if we just open it to the floor and see if anybody has any more questions, just quickly?
I hope that we can make a connection between the computer science group and the engineering group. I don't know what the connections are like exist already, but I can say that when I was at Swansea, we had a pretty strong connection to the engineering, because these are all done in conjunction with CFD simulation experts. This is not something we worked on by ourselves. So I hope that we can form a connection here as well between computer science and engineering. And maybe there is a connection that already exists, but I'm new here, so I don't really know what it looks like. But there might be an existing, and if anybody knows about an existing connection, I would be interested to hear about it as well. But if there isn't an existing one, we should create one.
Yeah, and hopefully events like this can lead to that.
Mm-hmm.
I think at the moment the connections are fairly ad hoc and more like a project by project basis.
Yeah.
So I know I'm just working with the research software team at the moment, but there's no sort of formal link there. But it's absolutely needed.
Yeah.
Because the results we get out a lot of the time are very difficult to interpret.
Exactly.
So maybe I could just ask a very general question then. The high dimensional data you're showing here is, it seems like when you're trying to interpret it, you very much deal with the dimensions that you started the problem with. You don't do any sort of projection. There's no like local linear embedding or principal comparison analysis or anything like that. That is the sort of thing that I would naively try to do, to try and visualize in a reduced dimensional space.
Yes, that's right.
Do you think that those sorts of projections and the methods that you use, how can they work together, do you think? Yeah, that's probably a very big question.
I think it's probably a very unpopular view of the dimensional reduction techniques. The problem with the dimensional reduction techniques, like principal component analysis and variations thereof, is the interpretation. So when you try to take a high dimensional problem and then reduce it down to, let's say, 2 dimensions on a scatter plot, I think the interpretation becomes very problematic. Like, how do you interpret those reduced dimensions? And then how did they relate back to the original space from which they came? That's another challenge. And so in the visualization group, in the visualization group, we don't really work on those in that direction. What we work on a lot is high dimensional visualization, and that's what the parallel coordinates is all about. The parallel coordinates style or visual design, it doesn't require that you reduce any dimensions. It preserves all of the dimensions, so you don't have to reduce them down. You keep them, and then you study the relationships between them. And then you can also see the connection, like in the example we showed with the marine turbine simulation. You see the connections directly between the different attributes and the spatial view. You can interact with those parallel coordinates and see exactly the correspondence between any CFD simulation attribute, any subset of any CFD simulation attribute, and its position in space. So you don't have to do any dimensionality reduction. I'm not a fan of dimensionality reduction, and I know that is an unpopular opinion. Like, most people love it, and they work on it a lot. I personally am not a fan of dimensionality reduction. I prefer to innovate high dimensional visualizations as opposed to trying to reduce them, if that makes any sense. Yeah, and we have done a lot. We have done a lot of work in high dimensional visualization. A lot. That could be its own seminar. Yeah.
Yeah, so I suspect a very interesting seminar as well. Maybe in the future we can organise a follow-up to this, and perhaps go into some of those techniques. I think that would be of great interest to the wider group as well.
Yeah, I think that the group would be very interested in that. I can also tell you that we've worked with the engineering group at Cambridge University on the high dimensional visualization side. So they're very interested in the high dimensional visualization side for CFD simulation, and we've worked with them on that aspect. Yeah.
Good. I think then if there's no questions from the rest of the attendees, we can all thank Bob for a very interesting talk and leave it there.
Thank you very much. I forgot to insert my virtual applause sound. Yeah.
Okay, I'm sure I will recording that.
Applauding in their minds. Thank you very much, James. Thank you, Rebecca. And thanks everybody that's watching. We are trying to record this talk, and we're going to record it and share it and put it online and all those things. Thanks you all. Thanks a lot. Thanks again.
Do you know where you're going?